Okay, what we're going to be looking at in this lecture, I'm going to review exactly why complex numbers are important in the context of computer science. So I'm going to go over some of the background material that was in the lecture that was uploaded earlier. So just to recap, we're going to look over the basics of complex numbers as they were presented earlier. I'm going to say a little bit about typical sorts of questions and approaches, you might say. Uh, I'll give a quick review of some advanced concepts, in particular the use of calculus with complex functions. Uh, Sorts of questions you might see in that area and how to go about tackling them. And I'll finish off just by reviewing exactly how complex numbers are used in computer science applications. So, the basics. Complex numbers ultimately originate as a justification for the claim every polynomial of degree k has exactly k roots. Of course, these are not necessarily distinct roots. Uh, the standard form we have for a complex number, which we write z usually, we have two real numbers, a and b, and we write our standard complex number form as a plus this object I multiplied by b, just to stress a and b are both real numbers. This object I, this is defined to have the property that when we square it, we get the same result as squaring minus I, and that result is minus 1. So, just to continue, review of the basic elements, uh, the number of forms we can use to represent complex numbers. So we have structures such as this 2 by 2 matrix form. We can think of them as two vectors in this object called the complex plane through this mechanism which is called an Argand diagram. We can think of them as pairs of numbers in a slightly different way as what are called by using what are called polar coordinates. And we have this very important final form, the Euler form, which relates complex numbers, the exponential function, and trigonometric functions. Uh, a number, we said we have the standard form, some real number a plus I multiplied by some other real number b. So we have what is referred to as a real part and an imaginary part. If we're using Euler or polar coordinate form, in the Euler form, we think of a complex number as some object r describing the size of the complex number, and that's multiplied by e raised to the power I multiplied by theta. Theta is referred to as the phase or sometimes the argument of the complex number that we're dealing with. And we can translate between these two forms fairly straightforward way. The size, this value r, is just the square root of the real part squared added to the imaginary part squared. The phase of a complex number, that's just the inverse cosine of the real part divided by the size, which is exactly the same as the inverse sine of the imaginary part divided by the size. So what sort of operations did we see? We saw the operations addition, this form of conjugate, and modulus, which is just another term for size. If we're given two arbitrary complex numbers, to add them together, we just add the corresponding real parts and the corresponding imaginary parts. This complex conjugate operator, all we do is if we had B was a positive real number, then in the conjugate it becomes the equivalent negative real number, and vice versa. The size of a complex number, as I mentioned on the previous slide, that's just the square root of adding the real part squared to the imaginary part squared. This is a positive square root, I should stress. For multiplication and division, little bit more involved. Multiplication of two complex numbers given by this expression. Division, or 1 over a complex number, all we do is we take the conjugate and we divide that by the size of the complex number squared. Typical sort of questions you might see, you might be given two example complex numbers such as this one and this one, and you'll be asked to give the result of adding them, or what the complex conjugate of one is, or what the size of one is, what the product is, or what 1 divided by one of the complex numbers is. You might get more involved questions, be asked to do something like simplify this kind of expression, 5 plus 2i divided by 6 minus I. And in order to do that, that's really just combining multiplication and division. So in order to simplify this expression, well, it's just 5 plus 2i multiplied by the result of 1 over 6 minus I. So we take the conjugate of 6 minus I, we divide it by the size of 6 minus I all squared, and that gives us this expression here, which simplifies to 28 plus 17i divided by 37. The denominator will always be a real value. The denominator, when we're simplifying expressions like this, will never be a complex number or a number involving I. What about more advanced ideas? So we saw things such as the root of a complex number, and a very important idea called the primitive roots of unity. Gave a brief overview of calculus extending to complex functions. So in particular, differentiating complex valued functions, integrating complex value functions. This notion of primitive roots of unity, this is very important in the formulation of the Fourier transformation. The last advanced idea here, integration of complex valued functions. This plays a very important role in advanced ideas in analyzing the runtime of algorithms or behavior of algorithms. So just a quick overview of what we described as primitive roots of unity. If we look at the Euler form of any complex number, that tells us if we take any natural number, then finding a kth root of that number, we take the Euler form of the number, we raise it to the power 1 over k, and that is just the size of the complex number we're dealing with raised to the power k, and then the exponential part, e raised to the power I multiplied by theta divided by k. And what that tells us is since the Euler form can be expanded as cosine of theta plus I multiplied by the sine of theta, and since the trigonometric functions are periodic, so their values repeat over intervals of 2 multiplied by pi, that tells us, first of all, there are k distinct kth roots of any complex number. And we find those distinct kth roots. Those are all given by using this term as the different powers to which we raise the exponential form. And these are particularly interesting in what may seem like a rather trivial case, in the case where we are dealing with the complex number 1. And these are called the primitive roots of unity, and all these are the k roots of the polynomial z raised to the power k minus 1. So, one of the issues with primitive roots of unity is that we're working in the complex plane. Now, it turns out we can develop an analog of these working with integer arithmetic. So what do we do here? We fix a pair of natural numbers, some natural number p and some natural number n. We choose a number base we're going to be working in, subject to the constraint that the number p is less than the number base that we're using. Now, if it's the case that when we raise p to the power n and look at the result modulo m, the number base we're using, that can be equal to 1. And what is happening then is our number p that we raise to the power n and get the outcome 1 modulo m. That's mimicking the way in which a primitive root of unity in the complex arena is behaving. So here's an example. If we have n equals 8, number is 2, and the number base we are working in is 17. Well, when we raise 2 to the power 8, we get the outcome 256. And 256 is an exact multiple of 17 with 1 added on to it. So 256 is 1 modulo 17. And what that tells us is that the number 2 is a primitive root of unity when we are working modulo 17 and when we are looking at primitive roots of 8 raised to unity. So overall, with the right choices of integer values, we can mimic the way in which the Fourier transform is implemented entirely with integer arithmetic. So an example question you might see, you might be given a value for for n, the power you're raising to. You might be given the number base you're working with. Normally that is going to be 10, decimal arithmetic. And you're asked to identify which of the options provides a primitive root of unity. So suppose your options are 2, 3, 5, 6, and 8. Well, in order to deal with that sort of question, to identify which of those is a primitive 8th root of unity, all you have to do is compute for each in turn that value raised to the power 8 and then look at it modulo 10, which in effect just means looking at the last digit in the number itself. So what we find in this case, that particular question, we take the value 3 and we raise that to the power 8. That's the same as squaring 81 because 3 raised to the power 4 is 81. And 81 squared is 6,561. The last digit of that number is 1. So that tells us that 3 is a primitive 8th root of unity when we're working with arithmetic modulo 10. What about calculus with complex functions? The extensions we need, these arise because the complex numbers are unordered. we looked at the notion of what has to happen with differential calculus, and the important point here is that the functions we are looking at need to satisfy what were called the Cauchy-Riemann conditions on the related partial derivatives. Typical question you might see may give a particular function, and it may ask which, if any, of the Cauchy-Riemann conditions that function satisfies. So you should make sure for that type of question that you can find whereabout in the notes the Cauchy-Riemann conditions are given. Don't try and memorize them. There's no point in doing that. For integral calculus, the way we view integration of a complex function is in terms of moving along some directed path between the 2 points we are integrating. And we approach that by thinking of a path as a real valued function called a parameterized curve. So if we're integrating between 2 points, P and Q, the way we deal with this parameterization is this is a real function, so a function which takes a real inputs and returns complex values, and all this has to satisfy is when we apply this function to the real part of the first point, we get the first point back. When we apply this function to the real part of our ending point, we get the ending point back. So this parameterization, this is a function from real numbers to complex numbers, which satisfies those two conditions. And as a result of looking at parameterizations, what we can show is that integrating a complex valued function over two complex valued ranges, that's exactly the same as integrating over two real values of this particular function here. So we apply the complex valued function that we're dealing with to the parameterization, and we multiply that by the parameterization, the first derivative of that function. So overall, that reduces the problem of complex integration to real integration. So an example you might see, you may be given some complex valued function, you may be given two complex numbers, and you're asked to identify which of a set of options defines a parameterized curve for that instance. You may be asked to reformulate the integral that's been given in terms of a particular parameterization. Then moved on to look at applications. One of the important applications was in this notion of quaternions. So quaternions provide very powerful techniques in three-dimensional graphics. Typical sort of question you might see is you'll be asked to identify which of a range of choices defines a unit quaternion. So just to recap, a quaternion is a four vector, four object. We have what we think of as a real part and a three vector, and this defines a unit quaternion if the square root of the result of adding the square of all the components, if that square root evaluates to 1. What you'll often see in the specification of quaternions is that these use trigonometric functions, and angles in the trigonometric functions are thought of as radians. So we have these standard relationships. Cosine of 0 is 1, the cosine of pi is -1, the sine of pi divided by 2 is 1, the sine of pi is equal to 0. We looked at something called iterated functions sequences. Another important application of complex numbers in computer science is in artificial intelligence and the specialist area called computer creativity. So, we're doing with iterated function sequences is classifying points in the complex plane according to whether these the size of a particular point becomes unbounded after we apply the function repeatedly. So these occur in computer music, in the work that Elaine Walker developed on chaos melody theory. They occur in CGI effects in a technique called fractal landscapes, and they occur in developing abstract images, what's called fractal set construction. So you might be asked, for example, typical questions such as to report the size after two iterations of some particular complex quadratic function, such as this one here. So just to summarize, why are complex numbers important in computer science? Well, the reasons are they have applications areas of algorithm analysis through this result called the generalized Cauchy integral theorem. They have applications in computer graphics through quaternions and realizing complicated three-dimensional effects, 3D graphics effects. They have applications in algorithmics by exploiting the form of the Fourier transform, which leads to fast multiplication algorithms, and it also provides a method of carrying out into image compression. Finally, they have applications in artificial intelligence in the area of computer creativity.